Okay. Good morning, everyone. Welcome to the third lecture of the series on statistical physics. So I'll briefly start by reminding what we achieved last time. So the goal of the lecture last week was to go from many species dynamics. So I'll remind you the equations that we derived from the generalized Lotka-Volterra model. Where the mu I are the relative abundances of the different species, normalized in such a way that the empirical mean of this guy is equal to 1. And gamma is the Lagrange multiplier enforcing this constraint. So here we had taken this as the parameters for the interactions between the different species. And in the simple case that we treated last time, we took that as being random Gaussian variables with mean 0, variance 1, and independent variable except for the pairs Zij and Zgi, where covariance is equal to gamma, with gamma between -1 and 1 that tunes the degree of reciprocal interactions between the different species. And this is a term that you could think about it as tuning the fitness, the individual fitness of the different species in their environment, and those were shown to be IIT distributed. And what we showed is that through something that is called dynamical mean field theory, this is completely equivalent when S goes to infinity, so S here is the number of degrees of freedom, to a stochastic process independent for each of the degrees of freedom here, that is written mu dot is equal to nu times gamma plus delta R minus nu. And so now we have to treat this term. So this term is a sum over many variables, which are weakly correlated because Zij and Zij and Zij prime are independent. This is a sum of many weakly correlated terms that ends up being represented by the Gaussian noise. That's a generalization of the central limit theorem. Plus, there is also an average. It takes the following form. And the correlation of the noise and this kernel in the delay response obey self-consistency conditions that are that psi tau phi to prime is equal to the average of nu tau nu to prime. So this is an average over the realization of the noise at fixed delta R, and then you average over the realizations of delta R. And R tau to prime is the response function. So this is a perturbing field. It's a response function of the average to a perturbation. Yes, thanks. And this enforces the fact that the average of nu is equal to 1, and this is enforced by gamma. So now last time, what I introduced was the phase diagram of this model, which has a very simple form in terms of the parameter sigma. That's for delta R is equal to 0 for all species. And there is a critical value sigma c, below which the system reaches a fixed point, and above which there are persistent fluctuations, and something that is reminiscent of the results by Robert Mage that we discussed last time. Oh. So now what I wanted to discuss was the properties of the system in this phase, where it's been the most studied. So what happens in a regime of, say, weak interactions, weak disorder in the interactions? So this phase can be studied using dynamical mean field theory, which is here. So we assume that the system converges to a fixed point. So nu tau goes to nu bar at tau to infinity. And therefore, from this condition, if nu goes to nu bar, you see that the correlation between psi of tau and psi of tau prime, if tau and tau prime are set to infinity, becomes independent of tau and tau prime. So psi, the noise which is here, also converges to a constant in time. So that's a Gaussian noise, not a Gaussian variable. And the variance of this variable obeys the same obeys the self-consistency condition here, which you can write like this in the fixed. The last point is that we expect, and this can be checked explicitly, that so now, for at a fixed point, we expect that the response function at late times becomes just a function of the time difference. So it's time translation invariant at late times. And so from these conditions, you can find the equation satisfied at the fixed point, setting this on the left-hand side equal to 0, and you get that nu bar times gamma plus delta R minus nu bar minus sigma psi bar plus gamma, oops, sorry, just need to correct something. Here there is a square. So now if you replace nu by nu bar, what you get here is the integral from 0 to infinity of this R infinity nu bar plus H H equal to 0. Where R infinity is equal to the integral from 0 to plus infinity d tau r of tau, where now r is understood as the function in the time translation invariant regime. So from there, you get that mu bar is equal to 0, meaning that the species is extinct, or, it's an or, mu bar is equal to gamma plus delta r minus sigma psi r divided by 1 minus sigma squared gamma r infinity. So you have these two solutions. And what can be easily realized is that if this solution is positive, then the dynamics at nu is equal to 0, the fixed point at nu equal to 0 is unstable, because there would be positive growth rate here. And on the other hand, if this is negative, this is clearly not an acceptable solution. So the right solution is the maximum of those two variables. So it's the maximum of 0, gamma plus delta r, minus sigma hat psi r, 1 minus sigma squared gamma r infinity. So what you get from there is that the first thing that you can compute is that the abundance distribution to add the fixed points it's a truncation to positive values of so you have delta r, so this is distributed according to some law, and this is a Gaussian variable. So it's the truncation of the convolution between a Gaussian and the distribution of delta r. In that sense, the distribution that you get is non-universal because it explicitly depends on the distribution of the disorder. Yeah.
So here you have a bunch of variables at 0.
Yes.
So how do I make, I mean, in principle, these are like, I mean, I can interpret this as some variables at 0, so that there must be a Lagrange multiplier that enforces that they are 0. But I mean, if I'm hitting a wall and I stick to the wall, so that there will be a force that prevents me to get on the wall. So
I mean, I would say that the force is.
what would you call forces here?
I mean, the force is this.
Is that
That term, which is negative. So it pushes towards 0.
okay, so it's the other side of the Gaussian.
Yeah. Yeah, exactly.
More down to earth. Let's start with 1,000 species.
Yeah.
Yes, 1,000. You compute this gamma and it's positive, you know, this maximum. So what does it tell you? How many species?
Yeah, so that's where I'm going. So indeed, so let's say that, for instance, if delta r is equal to 0, and you look at the p of nu, so there is the positive part, which is just a Gaussian truncated. So it would look like something like that. But of course, there is the as Paul mentioned, there is the contribution from all the guys that are extinct, right? Because some of them will go extinct, which is manifested by a delta peak at 0. And so there is a finite probability of survival. So regarding your question, there is a finite fraction of the species that you put initially that survive. It's equivalent to finite fraction of surviving species. So I'm going to call phi. And you can compute phi explicitly. So you need to compute the probability this guy is positive. And so if you write psi bar as being just a normalized Gaussian with variance 1 times the variance of psi bar, which we said is the variance of mu squared, which I'm going to call q squared, then you can write explicitly the fraction of surviving species as the probability that this combination is positive. So now it remains to fully characterize the fixed point phase. We need to solve for the self-consistency conditions of the dynamic ordinal field theory, which we haven't done so far. So you need to impose that. I mean, those are the same equations. I'm not going to write them explicitly. So you have this one for the variance. You need to impose that the mean of mu bar is equal to 1. This gives you just two nonlinear equations once you start from this distribution. You also need an equation to impose for R infinity. And because R infinity is the integrated response, and R infinity, you can show that, I mean, it's easy to get that if you had a perturbation, a steady perturbation, the integrated response is the linear response of the mean to this perturbation. And once you write this equation, you just add an h here, and you take differentiate with respect to h. You get 1 minus sigma squared gamma R infinity, but only for the surviving species. So this is the equation that you get. And I'm writing it explicitly because I'll use it afterwards. So you have this set of three nonlinear equations, three parameters to compute. You can solve it numerically. And you've completely characterized the fixed point. Typically, what you observe, as far as the number of surviving species is concerned, is that as you increase sigma, strength of the interaction, the number of surviving species will decrease. Until you reach a point which is sigma c, where this solution, which is the fixed point solution, is not correct.
So if I take the analytic continuation of that line, is it going to zero at finite sigma or is it going back to zero?
Yeah.
So I cannot recognize from just this I that some point where the function breaks down.
So what you no, actually no, not in this region. So maybe just a couple of remarks about this.
Sorry, what happens at sigma bar c? Sigma has
So sigma c is the point where the system does not converge to a fixed point. So here, essentially, to do this, I had to assume that you reach a fixed point. And I'm giving you, okay, if you reach a fixed point, in a way, what is the solution? There is a unique solution characterized by a unique distribution. It's this one. But what I'll show you next is that this solution past some threshold is not valid anymore.
Do you have an expression for sigma c?
Yeah.
Okay.
Yeah. I mean, if delta r, if all the delta r's are equal to 0, you can find it explicitly. Otherwise, it's still nonlinear. I mean, the solution of a nonlinear equation, which is a bit more complicated.
So in principle, there are like situations where if you modify that R or things like that, like for example, this like term in the equations that is just dependent on y, not the couplings between one or the others. In principle, you could make these fixed point equations having multiple. This can happen.
Yeah, you mean if you change the functional form?
Exactly. If you change the functional form, in principle, this point equation can have multiple solutions, and maybe you have multiple attractors, multiple points that you can partition your free space.
I agree.
And this has been found somewhere, or
In the symmetric case, it's been treated.
okay, but the symmetric case.
But
is,
within the IPFT, I'm not sure. But yes, in principle, then you will need to refine a bit this condition, because here also you see you have multiple fixed points. With the condition that tells you from linear stability which one you pick.
No, but I'm saying.
So you would need to refine this.
So I'm saying once you write the equations for R infinity and the correlation, the covariance of the noise, you have three nonlinear equations for three quantities, and in principle they can have multiple solutions, which would correspond to different surviving species profiles, like different attractors that partition your phase space depending on the initial.
In the solution of the DMFT.
In the solution,
not in the equations for.
So that would correspond to different attractors in the dynamics. That I mean, so where you go depends on the initial condition. So.
Yes. Okay. But I guess that's for small. No. Yes, you're right. You're right. No, this is not.
It cannot.
If that happens at sigma equal to 0, just at the individual species level, where the fixed point that you reach depends on the initial condition, then that will
Of that analysis, you depend on some initial condition. Here you presume that initial conditions are followed.
Yes. which I would say, for the lack of a better answer, turns out to be true when you compare to numerics. So that in that phase, you see that the fixed point that you reach is unique and independent of the initial conditions. Not only the distribution, but really the fixed point for a given realization of the matrix. And in fact, it was shown that the complexity of fixed points, of stables, I mean, the number of stable fixed points in that phase is exactly 1. So there is a unique fixed point which is reached by the dynamics here.
Kind of generally, in dynamical system, we expect if it's one-dimensional, like exotic f of x, yes, it would be just fixed point. If it's two-dimensional, x and y, we may have linear cycle. If three, the chaos. Because it's a union, you have here many species and just less.
Yeah, here it's a regime where there is just one fixed point. I guess the right answer to see that is that you have many species, but if sigma is equal to 0, it's a set of independent equations for the different species, which they all converge to a unique fixed point. Right? Exactly what you said, because you have one-dimensional system, so you converge to a fixed point. What that shows is that this is robust to some amount of disorder, and it breaks down past the threshold.
Sorry, one question. So, for instance, if you have, you say just independent, but if you, for instance, have independent, but one species, logistic equation, but noise, not the kind of noise you introduced, but demographic noise. I think about n as being discrete variable.
Yep.
So it's the number of animals. So there is inevitably demographic noise, and in those cases, generically, you get to extinction.
Yes. So here, I mean, here you will get to extinctions, of course, if you had demographic noise. Now there is a feature that if the amplitude of the noise is small, then essentially those guys are going to be killed quickly in a time that is logarithmic in the amplitude of the noise because they are doing exponential decay. And now those guys that are stabilized at a fixed point of order 1, I mean the ones that are here, will survive for a very long time. And what will happen close to here is that you have a leakage of species because you have species of very small abundances.
Well, those guys, sometimes they say that you get a solution is quasi-stationary. So it's
In the presence of
it's stationary, but
yes.
System time exponential in system size.
In the presence of noise, yes. Okay, so now 2 remarks. Coming back to things that we had said about generic empirical properties of many species ecosystem, that, okay, there is, I mean, it's trivial because it's a fixed point phase, but there is no fluctuations of population sizes, which is not the general rule in many species ecosystems. And there is no broad abundance distribution. At least unless those guys are themselves broadly distributed, but then you don't explain why you would have broad distributions. You would need delta R to be broadly distributed in the first place. Okay, so now I want to investigate what happens at this point and link it to what we discussed on May's argument about the stability of high-dimensional dynamical systems. So here, essentially, I made a fixed point ansatz, but it's like looking for the fixed points of a dynamical system. I never check that these fixed points are stable, right? And within the framework of DMFT, in order to assess the stability of the fixed point, we add to the deterministic dynamics a small noise. So of the form delta Ri goes to delta Ri as before, plus epsilon eta I of 2. So I'm adding a small environmental noise in the dynamics. So these are independent for different I's time translation processes, time translation invariant processes. And the idea is that when the fixed point becomes unstable, the response to these small fluctuations will blow up. So what is nice here is that, I mean, I did the full DMFT derivation, taking delta I as being random variables, independent, constant over time, but the derivation does not depend on them being constant over time. The only thing that I need is statistical independence between the different delta I. So actually adding this noise here doesn't change anything to the derivation. And so what you get in the dynamical mean field theory picture is pretty much the same thing as before, except that now you have to add the noise. And you have the same set of equations. I'm going to rewrite here. The average is equal to 1. The correlation function of the noise is equal to the correlations of population sizes. And this guy is the response of the mean to a perturbation. I'm gonna put h of tau here. So those are the same equations, except that now they have to be solved at epsilon, which is non-zero. So the solution of this equation is not the same, because you have to solve this equation now with epsilon, but still the functional form of these equations is identical. And now, assuming that the fixed point is stable, I assume that we have time translation invariance in the presence of small noise. So I'll say that R is a function of tau minus 2. we expect the TTI, so use TTI for time sensation invariant state at small noise. And now we play the same game that I used to describe non-stationary attractors of the local ultradynamics by defining the temporal averages. And if the dynamic is time translation invariant, this exists. And accordingly, z is the limit that goes to infinity of the log divided by tau. And once you do this, what you get is that z bar, or z, is equal to gamma plus delta r minus nu bar plus sigma hat phi bar plus gamma sigma square r infinity nu bar. That we had derived before when we looked at the generalized Lotkat ultradynamics. So there is a relationship between the value of the growth rate at infinity and the average time average population sizes. And so essentially, if nu bar is equal to 0, then z is negative. And if nu bar is positive, then z is equal to 0. So you get that nu bar is the max of gamma plus delta r plus sigma psi bar. So psi bar is accordingly the time average of the noise. And so what you get is that the equation for time averages is identical to the equation describing the fixed point phase. So if the fixed point is stable, the time averages that you get in the presence of noise are actually distributed exactly as the fixed point was distributed in the absence of noise. And now, now I've talked about the time averages, now I want to talk about the fluctuations. So we know decompose nu as nu bar plus delta nu, or let me write as nu bar plus epsilon delta nu. You also decompose the noise as psi bar plus epsilon delta psi. And if you look at what becomes of the DMFT equation in terms of this variable, I mean, you have that psi bar squared equal to nu bar squared on average. And then you have the same equation for this one, so you get that delta psi tau, delta psi tau prime is equal to the average of delta nu tau, delta nu tau prime. And now you can expand the equations of motion to linear order in epsilon. So to linear order in epsilon, and for nu bar positive, because for nu bar negative, you have delta nu, which is equal to 0. Yeah, because the variable is positive, if its mean is 0, then it's 0 everywhere. It's only for nu bar positive. You get that delta nu dot, so that's to linear order, is equal to theta tau minus delta nu tau plus psi delta xi tau plus gamma sigma square d to prime r tau minus to prime delta nu to prime. And this is the quick point solution at epsilon equal to 0. Because to leading order. This is what we have. And now, so this equation, it's linear. You can solve it in Fourier space. So it's nu bar omega plus sigma delta xi omega I omega plus nu bar 1 minus gamma sigma squared r omega. And now you can take the variance in the Fourier domain and use the fact that the variance of this guy and the variance of this guy are the same. This is contained in this equation. Hence, so if I define, introducing, so I'm going to write the variance of the noise, of the external noise, as 2 pi delta omega plus omega prime g omega. That's for the external noise. For delta nu, I'm going to write it as h omega. And so what you get from this equation is that h omega, you can relate now the correlation function of the population fluctuations to that of the noise as 1 minus sigma squared, the expectation of nu bar squared I omega plus nu bar 1 minus gamma sigma squared r omega squared. And this is times h omega. G omega, sorry. Now we have an equation that, to linear order, relates the fluctuations of the population sizes to the external noise. And what happens is that upon increasing sigma, the stability boundary is reached when there exists the frequency omega such that h omega diverges. And this is when the fixed point becomes unstable. So this happens first, it turns out, for omega equal to 0. And hence we get the stability condition, which is that 1 equal to, so I need to cancel this term to make omega blow up. Oops. So when omega goes to 0, the new bar cancel, but I need to recall that this is 0 if new bar equal to 0. So this is the expectation value of the theta of new bar. So I get phi sigma squared times 1 minus gamma sigma squared r infinity squared. And this is the condition to find the boundary of the fixed point phase. And obviously you need to solve in the fixed point phase for phi and r omega.
And sigma is sigma c.
Yeah, sorry. Sigma. Now there is one way to rewrite this equation using the solution for the fixed point phase that is, I find, particularly illuminating.
So this would correspond, so the physical quantity that are somewhere I and j, delta
Yes.
ui, delta j. So if I take the response of nu I with hj squared, somewhere ij, one over n,
Yep.
is this.
Yep. Yeah, because the noise is everywhere on each degree of freedom. So, yeah.
So this, you know, if there are cases where you get an instability, but still this is like there is no divergence on H. Do you know if there exists a case where you could have that the fixed point phase is unstable, but if you just do the linear analysis, you don't see any stability at the linear level, and it becomes unstable at the nonlinear level. Do you know if anybody?
In principle, it's possible. I'm not sure it's been seen, but maybe. So in the fixed point phase, we add obtain that R infinity is equal to phi 1 minus gamma sigma squared R infinity. That was one of the equations in the fixed point phase. And if I mix these two equations at the transition, what I get is that phi sigma c squared 1 plus gamma squared is equal to 1. We get this simple looking condition for the instability of the fixed point phase. And to understand where this is coming from, we can go back to May's original idea. And that you see is pretty robust. I didn't, like this is for instance, for any distribution of the delta R. distribution of delta R does not enter in this equation. So if you remember when we studied the stability of fixed points, what I had shown you is that the Jacobian at the fixed point of the many species system, J, was equal to minus D nu star. So this is the diagonal matrix of fixed point abundances times alpha star, and that's the interaction matrix restricted to the surviving species. And so now in our language, alpha star is the phi s times phi s matrix. Phi is the fraction of surviving species. There is only phi s surviving species. Alpha star. So it's 1 minus mu times the identity, the self-interaction term, plus mu u transpose, plus sigma square root s z star, where mu is the vector with only ones. So this is to account for the mean of the interactions. So if I look at the spectrum of this guy, so this will contribute only as an outlier, which is far outside of the spectrum. And these are Gaussian variable distributed with variance 1, mean 0, and cross correlations gamma between elements across the diagonals. And so what I'm going to say is that I'm going to assume that the Bell spectrum of Z star is the same as in the original ensemble, now with size phi f times phi s. The meaning of this assumption is that when I construct the matrix Z star, I'm not taking a random restriction of the original matrix. I'm restricted to the elements that survived the selection process that went on during the dynamics. So here what I'm assuming is that the statistics, the changes in the statistics of Z star due to this dynamical process do not alter the bulk of the spectrum. But the bulk of the spectrum is sufficiently robust to these changes. And indeed, it has been shown. So this is equivalent to saying that dynamically induced correlation are too weak change the bulk. So now if I do that, and I look at the spectrum of alpha star, so that's the in the complex plane. So this is the spectrum of alpha star. I have this diagonal component at 1 minus mu, and outside I have an instance of the elliptic ensemble. So the spectrum would have points uniformly distributed here. And the ellipse here has dimension 1 plus gamma sigma square root phi, and in this dimension 1 minus gamma sigma square root phi. So if gamma, for instance, is equal to 1, you see that the spectrum is real because the matrix is symmetric and you recover the inner semicircle. If gamma is equal to -1, then the spectrum is purely imaginary, and you also recover the entire semicircle along the imaginary axis. And this ellipse interpolates between the two regimes. Hence,
Otherwise, for any eccentricity, it's just uniform.
it's uniform inside the ellipse. Yeah. Hence, the fixed point becomes unstable for one plus gamma square sigma 1 minus mu square phi is larger than 1. And this, if you recall, sigma at was exactly sigma divided by 1 minus mu. So we recover by this simple argument, let's say a la May, exactly this condition that we get from the ellipse, unifying in a way the two perspectives. So now, before the break, I'll just would like to make a comment on experiments that have been done with microbial communities that tend to support this picture inherited from random interactions, let's say, in high dimension. So the paper I want to call that is emergent phases of ecological diversity and dynamics mapped in microcosms. Switch to Eval 2022. And so what the experiment is about is that essentially in a test tube, they make synthetic bacterial communities using a library of 48 bacterial isolates. So there are 48 different types of bacteria. And they make communities out of that. Doesn't need to be 48 bacteria at the same time. I mean, it can be like 2 species, 4 species, 8 species. And And essentially, they let these communities grow. They do serial growth and dilution, and they monitor the evolution of the population sizes of the different type through time. And what's a bit the tour de force of this work is that experimentally, they can tune the level of interactions between species by changing the concentration of chemicals in the medium. So mainly glucose. In the medium. And that tuning, they did that by 2 species experiments, where they see that increasing the, the concentration of chemicals tend to increase the fraction of pairs, where one species completely outcompete the other, meaning that it tends to increase the strength of the interactions between the different species.
But so it's more like
I mean, resource consumer. So, I mean, I don't know what you, because anyway, the local ultra model is phenomenological. So it doesn't tell you about what mechanisms induces the interactions. So you could say, I mean, yeah, they interact through chemicals, which are the resources that they feed, but also chemicals that they release. They can release toxins, for instance. So then the outcome of the interaction, and they can change the pH also of the medium. So the outcome of the interactions is the synthesis of these different pathways of interactions, I would say. But in this picture, at the very qualitative level, going to resource consumer model wouldn't change the outcome. So essentially, they have 2 control parameters now, which is S, so the number of species that you put in the community, and the strength of interactions. And so in the random interaction picture, the stability condition writes, if I'm rewriting the same condition as before, so it's so first I need to give you the value of sigma c. So sigma c is equal to square root 2 divided by 1 plus gamma when delta r is equal to 0. So the stability condition becomes that the standard deviations of alpha, the interactions, divided by 1 minus the mean of alpha times the square root of the number of species that you put in the community is less than square root 2, 1 plus gamma. So a number of order 1. So here you have the species pool size. And here you have the strength of the interactions. And and what they showed experimentally is that increasing the number of assembled species or increasing the strength of the interactions led to an increase in the fraction of communities that display fluctuations in population sizes, which is consistent with this picture. And I'll stop here for the first part of this lecture, and then we can go for a break.
What that star was?
Ah, so Z is here. So yes, so alpha is the interaction matrix. I said that alpha star is the interaction matrix restricted to the surviving species. And the way I had decomposed it was alpha is equal to the mean plus sigma divided square root S times Z, where Z is the part that the random part of the interaction matrix. So Z star is the restriction to the ones that survive. The restrictions of Z to the one that survive.
So, I don't understand what they really checked. They checked that some region where there is something point and more one, or they checked the relation.
So no, I mean you don't have the argument is a purely qualitative level.
Okay, because the relation depends on gamma.
Exactly. No. It's qualitatively consistent with the picture that emerged from May's ID, let's say, in high dimension.
What would that been like the alternative?
If you have very structured interactions, for instance. I mean, what? If you have very structured interactions between the different species. Like here, it's if you don't have all-to-all interactions, if you have just pairs of competing species, for instance, or if the species were interacting only through, if there was only pathway of interactions, so it's, let's say a single resource, for instance, then you don't get this phenomenology because essentially the matrix of interactions becomes rank 1. So that's compatible with a matrix of interactions that is full rank, I would say.
But I mean, this depends on how they construct the thing. I mean, things like random bacteria that interact with the same chemicals and so on, that you would expect.
You would expect that you need to show it experimentally.
No, but you start with one species and then you add species like one by one, by one. At some point, I mean, very natural. I don't see any other scenario where, I mean, having a structured interaction is much more fine-tuned than having something that's structured. So when you add, so I don't understand what's like the. I mean, if you show me something, so either there is an alternative view that is the naive one, and this is like naive, but this is the number one. So I don't understand what would be like the naive alternative view that you would expect.
I would say that the idea that you can reliably predict the dynamical outcome of an assemblage of bacterial species from just coarse-grained properties of the interactions, so the number of species and the typical level of interaction strength, is not something that is. I mean, you expect it from this random picture, but it's not something that is obvious. It's not something that is obvious in the ecological community.
I mean, you see that this equation for the critical point is just checked qualitative, not quantitative. So what do you mean by saying quantitative? When you say that you check it, what do you mean? It's just going to come to fluctuations. So,
and I'll say more afterwards, but yeah, essentially that's it.
Well, for instance, imagine that you have this S definition species, very deep. But in all this picture, number of survival number 5 times S. But it could have been still large, but still like square root. Yeah, but so if, for instance, experiment would find something like that, of course, with 48 species, it's very hard to distinguish. Exactly. But in principle, you know, especially bacteria, if thousands.
So it's an unclear thing to check. So
yeah, but that's not been checked. That's
not been checked. Okay.
But you could imagine another scenario where you start packing species, right? And And at some point, you reach a point where they start excluding each other. So you have one species that survive, two species that tend to survive, three species, one would go down. You had another species, one would go down, and you stick to a state where they're not able to sustain a large number of species, and you don't have this behavior. That would be possible, right? If you put a large number of species, how large is the number? You would always find that in the end you have two species coexisting, and they're extinct. And that all the others have been driven to extinctions.
But then it depends how you what, no? But by small amount, then this all them at random, just equal amount. I mean, yeah, maybe you have sometimes that just survive, sometimes 10. I mean,
If it's random, but a finite number, yeah, maybe sometimes it will be two, sometimes five. Upscale. Yeah, maybe even logo fans, you know.
so that's why I'm asking what its quantitative check.
No, there is no
Very, very hard to check.
there is no quantitative check whatsoever.
Okay, for that.
To break? Okay, go.
Okay, so now I wanted to discuss what happens in this system when you go past the transition, which is something that, I mean, this, for instance, May's argument that we're discussing earlier does not tell you. What happens in the fluctuating phase? And so what numerical simulations have shown here, the reference would be this one. And so Roy, Yuri, Union, and Marotta, and I'm writing all the authors because I don't remember the name of the journal in which it was published, so it will be easier to find with the complete list. So what these numerical simulations have revealed that the dynamics in the fluctuating phase is not time translation invariant. So it is aiding with the correlation time that grows linearly with the elapsed time. And that was shown in a work I did with Gagnon. So, and that interesting fact, and I want to stress it now, I think is probably the most distinctive feature of this class of models in high dimension, in the sense that the stability to fluctuation transition that we discussed, you can understand it in the May framework, and it doesn't rely on anything that is specific to population dynamics. In fact, it happens in every sort of randomish dynamical system in large dimension, neural networks, for instance, or others. This is quite specific to what's happening here. It's been found in other models since, or other classes of models that still respect the fact that you have extinctions, so sort of this distinctive feature of population dynamics, and it's generic. The fact that it's aging and not DTI is something that is generic once your disorder is strong enough. So in practice, what that means is that if you measure the correlation function, which is, so if you do a simulation, then that you can write it back in the DMFT language, but the empirical correlation function of population sizes as a function of delta tau. You will find something like this. So this is increasing tau, so increasing the elapsed time. And what I mean by correlation time that grows linearly with the elapsed time is that if you plot the same data now as a function of delta tau divided by tau, you obtain a clean collapse. of the different curves. On the other hand, oops, if you look at what's happening for the dynamics of the different degrees of freedom, you take a representative degree of freedom, pick one at random, and you look at the logarithm of the population size as a function of time, you will see something like that. It goes down, and now it's order 1, and it goes down, order 1, it goes down. And this defines an envelope that is linear in tau. What that means is that the aging dynamics is accompanied by ever larger fluctuations of log population sizes. And, and in a sense, the fact that these two things go together is consistent with the idea that I think, last week or 2 weeks ago, that so TTI correlations, that there is an equivalence between TTI correlations of population sizes and long time convergence of the log population sizes divided by the elapsed time. If you have TTI, if you have time translation correlation of population sizes, then you have long time convergence of this, and reciprocally. So here you see the two things break down at the same time. Because since this goes down with tau, this guy keeps fluctuating as time goes on. It doesn't converge to fixed time. And so maybe I can say that this behavior generalizes in a robust way. And I'll be a bit more explicit later. In a robust way, the heteroclinic cycle in May Leonard 3-species model.
What is the conclusion then? Are you saying that all this class of model is not realistic due to this aging? Or are you saying that in nature we observe aging?
So, okay, so now you're right, I'm only discussing the model, and when you see that, you're thinking there is something wrong, and I agree with you. So, maybe if you let me continue for a while, or 2 minutes, I'll go back to your question. I'm planning to answer to this question. But in nature, okay, I can say in nature we don't observe aging. That I can tell.
What kind of, if with my learn of the species model, there were no randomness at all.
Yes, there was no randomness, and you needed to impose some cyclic structure of the interactions in order to see it emerge. Here, with random interactions, with probability 1, let's say, that emerges out of the randomness.
It's like Toulouse thing. Toulouse was doing the same thing on spin glasses. You look at the frustration, a measure of frustration. It reminds me that the thing of May and Leonard is like you look at like triplets of cycles, and then you can measure frustration. Here it's dynamical frustration in a sense. So maybe one could do the Toulouse analysis,
Maybe.
which would be like checking this condition on higher and higher. So a question. So is it true that one can interpret this as like some quasi-equilibrium from fixed point to fixed point, quasi-fixed point to quasi-fixed point, or that's completely wrong?
So that's, I think, yes, in a certain sense, that if you look, so okay, that was pretty much where I was going. So if you look at any instant of time, one can separate the system between abundant species and by that I mean nu I of order 1 and rare species, very rare species in that case. So it's the logarithm of the population size minus is of order, so exponentially small in the elapsed time, order time. At late time, of course. And so what you can say is that the abundant species and this might answer your question. So obviously, since correlations of nu become slower and slower, that means that the speed of the dynamical system, the time derivative of the different abundances, becomes smaller and smaller. So the abundant species are found close to a feasible, stable fixed point. And the number of abundant species is strictly below May's bound. So this condition of the fraction of surviving species, there was a condition of the fraction of surviving species for a given value of the disorder. So you are strictly below this. So in practice, what happens is that if you take at some point, you put a threshold, very low value, 10 to the minus, I don't know, 20, I don't know, whatever. Doesn't really matter as long as this value is small and doesn't scale with time. You kill all species that are below, and you let the system evolve past that threshold. What you will find is that the system converges to a fixed point, and that the distance to this fixed point decays as 1 over the elapsed time as time goes on. So that's the measure of how closely you are to the fixed point. What you cannot do in finite time as s goes to infinity is to interpret the transition as discrete transitions from fixed point to fixed point. Because what I was going to say is that the fixed point is, however, invadable and some of the rare species are exponentially growing. So this is some of the rare species. This one is very small, but here it's exponentially growing. So some of the rare species are doing that. And thus destabilizing the fixed point after long enough time. And what I mean by that is that once this species, this degree of freedom arrives here, it's going to induce perturbations on all the degrees of freedom that were abundant, and this will drive some species towards extinction, and that's what sort of keeps this motion going. But you cannot really interpret it as a discrete and isolated transition from fixed point to fixed point. It's more a continuous flux of rare species that continuously move the fixed points. That's the DMFT picture.
But if I reparameterize, I mean, if I use as a clock of the dynamics some distance in phase space, instead of looking at the dynamics, its clock, natural clock, just use as a clock like the distance between configuration. Would I get like the right picture?
What do you mean the distance?
So I mean, I say, okay, imagine that I look at the system at time t is in some configuration, and then I define a measure of time. Instead of looking at time, I say, okay, I look at the elapsed distance from this configuration to another one. So I mean, I look at the overlap, for example, between two configurations. Then I can use this directly as a clock of the dynamics. Then being that it's like some transition from quasi-equilibrium to quasi-equilibrium, that I can rewrite the dynamics using this. I mean, you are saying that it seems that it's representation violent, because when you plot it as a function of delta tau over tau, means that there is no natural clock.
Yeah.
So the only clock is just how far I am from a given configuration. I can use the distance from one configuration to another configuration as the natural clock of the one.
That I think I mean, if you want to really see, I don't know, if you really want to see discrete transitions, I think you will need to go to timescales that are not accessible within the MFT. That's my hypothesis. Because within the MFT, you can show that, and that's what I was going to do, that in order to take care of this linear scaling with tau, you can go to log space of time and show that the dynamics becomes time translation invariant in that log space. But still, it's continuous. So you have continuous variation.
It's always continuous. That's I mean, it means that if I look at the distance between configurations, it's a continuous type. So I mean, this doesn't mean that if you write things this way, you get some discrete jumps. Everything is continuous, but the right time is just a question.
Maybe. I don't know.
When you're saying within the MFT.
Yeah.
So for instance, we can see the assumption no either. We know that if it's from complete graph, it's perfectly okay. But from details, if you can see the complete graph, fine inside there. And on either 1D, 2D, 3D, it wouldn't. But you say within the MFT, this knowledge is that it's actually asymptotically exact, right?
So,
Or not?
so there is an order of limits that you need to take.
Yeah.
Is that for the MFT to work, you need to send the number of degrees of freedom, so the size of your graph, to infinity before taking time to infinity. So it's finite time, even though possibly arbitrarily large, as long as it doesn't scale with the system size. So if you want, the MFT would allow you to, if you think about the Ising model on the complete graph in the ferromagnetic phase, you could describe fluctuations within one basin. You start with plus fluctuations around that, but you wouldn't be able to see within the MFT the barrier crossing and go to reverse magnetization. This is what I mean by the range of time accessible to the MFT. Except that here it doesn't have to be scaling and barrier crossing type scaling of time.
Sorry. There is any particular behavior of the sides of the, for instance, of the plateau where there is abundance, or I mean, in terms
Yes.
of time.
So I mean, because I mean, it's the same thing that. Okay, from this picture it's not so clear, but basically this, I mean, these times
Increases.
also this time, yeah,
Okay.
scales with the elapsed time.
Okay.
And all, I mean, also this one, typically, the dynamics is stretched like
Okay.
and so. To understand the origin of the dynamical slowdown, so we can go back to DMFT equations, dynamical mean field theory. So in the simplest setting, for gamma equals 0, and delta R is equal to 0. So what we found was this, nu dot is equal to nu, gamma minus nu, minus sigma xi, psi xi. So the correlation function of xi is equal to the correlation function of nu, and nu is equal to 1. So that's the simplest setting. And now what I want to introduce is the log time. Because if the correlation function, or if the system is aging through correlation time that grows with the elapsed time, it's equivalent to saying that its time translation invariant in logarithmic time. And z, as before, it's log of nu divided by t. Okay. And I'm going to make an assumption and so this divided by time aims at rescaling the vertical axis of this curve. And I'm going to make an assumption that I'll verify is in a way self-consistent, which is that the correlation function of the noise, which is the object I have to solve for, is time translation invariant in log time. So this is going to be my assumption. So assumption psi s prime is equal to c s minus s prime. C is some regular function. I'm assuming that the noise is time translation invariant in log time. if you do this, what you get is the following equation directly from this one, that dz ds minus z plus gamma minus sigma psi of s minus e of exponential s z of s. So this is new part. And this, as s goes to infinity, this has the interesting feature of, so if I take z to be negative, this is 0. And this guy is plus infinity if z is strictly positive. So what you get from that is that the self-interaction term, so this minus nu, which is here, and which you find here, acts as a hard wall confining the dynamics to z less than 0. And you get dz ds is equal to minus z plus gamma minus psi of s minus, so this is the hard wall, if in the language of, I don't know, Langevin equations, that I would call a hard wall potential. And so the result is a non-Markovian random walk. Non-Markovian because this guy has memory, a priori, with a drift. In a confining potential. And the confining potential is harmonic if z is negative, and otherwise it's a hard wall at z equal to 0.
So I'm always confused by this. So maybe you could.
Yes.
I mean, when you look at this term that or infinity, I mean, this is asymptotic, but there is always, I mean, there should be a matching between 0 and infinity.
Yes.
So there should be a scaling term that controls the dynamics close to the wall.
Yep. Yep. I mean, essentially, I mean, this is where I was going, but since this guy is continuous, so to ensure confinement, at z equal to 0, the thing that you need is that mu of s, which is w prime of z of s, as I wrote it, exactly compensates for the driving term here, and is gamma minus sigma psi of s. And this is essentially the value of this guy when z is equal to 0. And so you get that nu of s is theta z of s times this guy, where theta is the Heaviside function with convention that theta of 0 is equal to 1. And now the self-consistency of the ansatz that I made, meaning that assuming that this guy is time translation invariant in log time, so the resulting, we can write the resulting DMFT equations. Which are that psi s is equal to nu s prime, nu s prime. And this you can write it for this equation. It's theta z of s, theta z of s prime, gamma minus sigma psi of s, gamma minus sigma psi of s prime. And you have also that theta z of s, gamma minus sigma psi of s is equal to 1. So the self-consistency is about the fact that you assume that this guy is time translation in log space. You write the dynamics for z, you get the dynamics for nu, and then you will get something for the correlations of nu that is also time translation invariant in log space. Obviously, these equations, and obviously it's not obvious, but it turns out that these equations cannot be solved exactly analytically. The resulting equation for the long-term dynamics in logarithmic time.
So you are saying that nu is really a theta. There is no scaling function in the zero.
As time goes to infinity. That's the, I think that there is a limiting process that describes the long time behavior.
Because that's fascinating. Because what I would have expected that you get this theta times the gamma thing, but then this is true only if this gamma minus sigma c is sufficiently far from 0. So if it is close to 0, there should be a scaling window that depends on s. I mean, bigger s, that's the smallest the scaling window, where you should have a non-trivial scaling function.
I agree.
And
But the thing is that you don't need to describe that to solve the DMFT.
Exactly. That's what's surprising me, because in general this scaling part is the one that at some point it will pop out somewhere else.
Not here. Not here, and I think that's because the dynamics is uniformly slow. There is no fast time scale in the dynamics.
But that scaling function is precisely the part that makes this exponential growth very rare. These species that have become very small. That scaling function captures the exponential growth.
Yeah.
So, and it's clear that that scaling function is driving the dynamics. So it's strange that it's there, but in your answers you don't see.
So there are some problems where you need to take care of this, if you want to answer other questions. But at the level of dynamical initial theory, you don't need it.
But you agree that dynamics where you are very small and then boom, exponentially fast you grow to 1 is what is driving everything.
So no, because you captured the exponential part. What you're missing is
So the initial part, the exponential part is precisely that scaling function. And you don't have, it's like, I don't know, like, it's like getting work from zero energy. I don't know, you know. It's something that seems relevant, but you don't get from the analysis.
That's because this thing that you're describing becomes instantaneous in the long time regime, in logarithmic time. That's the reason why you don't see it. These equations, they cannot be solved exactly, but you can solve them numerically. I mean, there are procedures to, once you have these equations, you feed a noise for certain correlation, you compute the resulting correlation of nu, and you iterate the process until convergence. So you can solve them numerically and check that it gives the right thing when you compare it to the simulations of the many species dynamics. So we don't have this analytical solution.
So what are so can you compute, for example, scaling function? So if you compute, so this is already in the S to infinity. So you're saying if I solve these equations are already in the T to infinity.
Yep.
So you can compare this with finite numerical integration. And has anybody?
Yeah. And it works. I mean, you see the collapse of the correlation function. The collapse of C as a function of delta tau divided by T. You can see it at finite time, and you can overlay this correlation function.
So you solve this, and you get the so this you see already at times that are relatively small, or you need to go to very large time.
You need to go to quite large times. I mean, if the simulation that we did were with like, I think the biggest simulations were 20,000 species and time up to 20,000.
Okay, so you did simulate, but I think you try to solve DMFT numerically.
What do you mean?
So instead of doing the simulation, you solve the MFT with the transient.
No, because with the transient, the dynamics become slower and slower. So you need a mechanism that adapts the time step of the MFT to the slow and slow growth, which is sort of equivalent to going into log time. So you sort of impose this from the get-go if you wanna solve for long enough time.
But if this is correct, say that this log grid stable.
Yes. Maybe a second remark. To ask for the Ney-Leonard model, and that goes along what Sylvain was asking. Coexistence in this phase is pathological. Because the deterministic dynamics drives every species arbitrarily close to extinction. So we have an extinction mechanism that is not in this continuous picture with just ODEs. You get the rapid extinction of many species. And in fact, what's interesting is that the effective, to start having extinction, the effective number of species S goes down, right? Meaning that the effective sigma hat, which is proportional to square root S times the standard deviation of the coefficients of the interaction matrix. And this is what controls the position in the phase diagram. This goes down. And this keeps going until the system re-enters the fixed point phase. So not only coexistence is pathological, but the mere existence of these fluctuations is also pathological, because the system finds, once you have extinctions, the system finds a way to suppress species and suppress what's feeding those extinctions, those fluctuations, eventually leading to a fixed point. And I think I should stop here. Otherwise, I'll give it too long. I'm sorry if I didn't really answer your questions. So maybe I can comment a bit more, and I'll do that in detail next week. So if you want to, there is one mechanism by which you can sort of save those fluctuations, which is by killing the absorbing hyperplanes of the dynamic, which is what effectively generates this heteroclinic behavior and this agent. So you can kill it by adding an external migration rate to the system. So essentially, by writing that, okay, the dynamics is nu I dot is equal to nu I times what we had before, plus lambda. I'm not saying where lambda is coming from, but as I was discussing in the first lecture on a single species model, this could be viewed as a very crude mechanism for accounting for the presence of space. So you are looking at something somewhere, and individuals come from the outside. What I'm assuming here is that this is fixed, and I'm not telling you why this would be fixed. So this is what's lacking in this lecture. If you do this at a very small lambda, effectively, now if you look at the logarithm, here you have log lambda, and you do something that is quite similar to the dynamics at lambda is equal to 0, but now this stops the aging mechanism by putting a lower. And you get a typical time scale that scales with the logarithm of lambda, which is the time it takes for exponential growth to go from 1 to lambda and from lambda to 1. So that I'll discuss a bit more in detail next week. What's interesting is that, and maybe I can comment on that to conclude, is that what I didn't tell you in the experiments that I was discussing before, is that in the experimental setting, there is explicitly the migration rate, which is constant for every species that are present in the community. And there you do see fluctuations. What they showed is that if you don't put this term, and that was done in a later paper, then the fraction of community that effectively fluctuates is dramatically lowered, even though this guy is extremely small, what they were putting in experimentally compared to the total size. So that those two things seem to point toward the relevance of migration, hence the relevance of space, in order to explain sort of dynamical many species fluctuating states. But that will be for next week, and then we'll stop here today.
Questions?
Including the log scaling, your first argument was like numerical simulations. Is there analytic things we could have seen in the DMFT equations that pinpoint to that log scaling, like from the start?
So, I mean, from this,
or is it like you introduce that scaling and it comes to be relevant?
so if you want, once we introduce that scaling, you realize that there is this natural dynamics that emerges from the DMFT equations, where you get rid of the elapsed time and everything becomes, if you assume that the solution of the dynamical mean field theory equation is time translation invariant in log time, then you do see that, I mean, this is effectively what you get, that the dynamics that it produces is time translation invariant in log time. Maybe the intuition for that is that that's a generic property of log-time ultra, or the system with multiplicative noise, that if you have aging in the populations, then you have this z variable, which is not that does not converge at late time. So this pinpoints to the fact that this is the right variable to look at. Then just from the get-go, from the dynamical mean field theory equation, saying it will lead to aging. I mean, once you've seen it and you've done it, yes. Before that, I don't know if there was a good argument to say so.
More questions? Okay, so.
No, thank you.